Supersonic Travel and the Doppler Effect. In this lesson, we'll be talking about the Doppler Effect and Doppler Shift, calculating observed frequency, applications, supersonic travel, Mach speed, supersonic flight, sound barrier, supersonic travel, and sonic booms, as well as vapor cones. The Doppler Effect. The Doppler Effect is the change in the frequency of a wave due to the motion of the source of the observer. So if you're going towards or away from a speaker, you're going to experience the Doppler Effect. If a car is coming towards or away from you, you're going to experience the Doppler Effect. So example, moving cars and trains, rotating whistle, light waves, these are all things that experience the Doppler Effect. As the wave approaches the observer, they become compressed, shorter wavelength, and you can see that with the picture here on the bottom, with the man on the right-hand side. So you can see how the waves are closer together towards him, and further apart to the woman on the left-hand side. And you can see the wavelength represented as well. So as the wavelengths are closer, a higher frequency is going to give a higher pitch. Now this can occur if you're going towards the speaker or away from the speaker, or if the speaker is coming towards or away from you, or in this case, the ambulance is coming towards or away from you. The frequency of the sound source differs depending on the observer's location. The frequency of the police siren is higher for person A, so person on the right-hand side, than it is for person B, because the siren is going towards person A in this example. Now the reason this occurs is because every time the siren is emitted, the car is moving in that same direction. So if the car was stationary, it would be emitting sound waves uniformly all around it. But since, in this case, the ambulance is moving towards the right, every time it emits a sound, the ambulance is also moving in that same direction. So the waves are going to get compressed. The second wave is going to be emitted closer to the first wave than if it were just standing still, because the car is moving in the same direction as the sound wave. And if you look at the left-hand side, we're actually moving away from the previous sound wave. So that's going to give it a bigger gap between the sound waves that are emitted. And keeping in mind, frequency is simply cycles, or in this case, waves per second. You're going to see more waves per second on the right-hand side than you're going to see on the left-hand side. Calculating observed frequency. Observed frequency can be determined using the following formula. F2, which is the observed frequency, equals F1, which is the produced frequency, times V, which is the speed of sound in the medium, divided by V, which again is the speed of the sound in the medium, plus or minus Vs, which is the speed of the source through the medium. V plus Vs is used when the source is moving away from the observer, and V minus S is used when the sound is moving towards the observer. So in this case here, this would be V minus Vs, and this one would be V plus Vs. And that's just something you got to keep in mind. Now, a good way to remember that is the left side is going to equal to the right side of the equation. If we have a bigger right side of the equation, we're going to have a bigger left side of the equation, or a bigger observed frequency. So to find a higher observed frequency, we need a higher F1. Now to get a bigger F1, we need to have a lower denominator. If your denominator is lower, you're going to divide by a smaller number. That's going to make the right side of the equation bigger. How do we make that denominator lower? We're going to make V minus Vs be used. So V minus Vs is going to make the right side bigger, which is going to make the left side bigger, and V plus Vs is going to make the right side lower, and therefore the left side lower. Check your understanding. A truck traveling at 100 kilometers an hour sounds its horn as it approaches a pedestrian standing on the highway. If the car's horn has a frequency of 440 Hz and the temperature of the air is 0 degrees Celsius, what is the frequency of the sound waves reaching the hiker? A, as the truck approaches, and B, as it has passed the pedestrian. So pause the video and try this question. So the first thing we need to do is figure out what our Vs is, and that's this one right there. The Vs is the velocity of the source. Vs is going to equal to 100 kilometers per hour. We need to multiply that by 1 hour, or 3,600 seconds, times 1,000 meters over 1 kilometer, which is going to equal to 27.8 meters per second. So we got our Vs. Our V is going to be the speed of the sound, and then we're going to use this equation. So it'll be 332 plus 0.59 times 0, and that's going to give us a speed of 332 meters per second. And now we can answer the question. So we're asked for what is the frequency of the sound waves reaching the hiker. So we're looking for F2. F1, if you remember, is the produced frequency. So F1, we're told, is 440 Hertz. So now we can plug our numbers in. F2 is our question, is equal to 440 times V, which is 332, divided by 332. Now, the truck is approaching, so the frequency is going to be higher. So it's 332 minus 27.8, and that gives us an observed frequency of 480 Hertz. And that makes sense. As the vehicle approaches, its frequency is going to appear to be more than it actually is. It actually is 440 Hertz, but the perceived frequency is 480 Hertz. So that's A. B says after it passes the pedestrian. So that's going to be the exact same thing, only we're going to add 332 plus 27.8. So F2 is going to equal to 440 times 332 divided by 332 plus 27.8. That's going to equal to 406 Hertz. As the vehicle is moving away from you, its perceived frequency is going to be lower because the waves are going to be stretched out. It's going to look a lot like person B here. As the vehicle moves away, the perceived frequency is less than when it's coming towards you, as is the case with person A. Now we should have two sig digs in our answer, so our final answers become 4.8 times 10 to the 2 Hertz, even though 480 Hertz is actually correct, and 4.1 times 10 to the 2 Hertz. Check understanding. A truck sounds its horn at 502 Hz as it approaches a person by the side of the road. The person has perfect pitch and determines that the sound from the horn has a frequency of 520 hertz. If the speed of sound that day was 340 meters per second, how fast was the truck traveling? So use this little cheat sheet down here to answer this question. Okay, so what do we know? A truck sounds its horn, so that's the produced frequency. So F1 is equal to 502 hertz. As it approaches a person, so it's coming towards, so write down on here too, the person has perfect pitch and determines that the sound from the horn has a frequency of 520 hertz. That's the perceived frequency, or the observed frequency. So that's going to be F2, and that's going to be 520 hertz. If the speed of sound that day was 340 meters per second, which is going to be V, the speed of sound in that medium. So V is going to equal to 340 meters per second. How fast was the truck traveling? That's going to be Vs, the speed of the source. Now we can plug our numbers into our formula. So F2 is 520 equals F1, which is 502, bracket V, 340, divided by V, 340. It's coming towards us, so it's minus, and then we're looking for Vs in the question. Now there's a few ways to tackle this problem. What I'm going to do is I'm going to multiply the 502 by 340, and then we're going to simplify it after that. So 520 equals 502 times 340, and that equals to 170,680, and that's all going to be over 340 minus Vs. So now we need to get Vs on its own. So what we're going to do is we're going to multiply both sides of the equation by 340 minus Vs. That's going to cancel it out on the right-hand side, and we'll be left with 340 minus Vs times 520 on the left-hand side. So 520 times 340, that's just that multiply, is going to equal to 176,800. And then 520 times Vs is just simply going to be minus 520 Vs, because we have a minus in front, so we got a minus there. And that all is going to equal to 170,680. We're going to bring that to this side of the equation, this guy to that side of the equation. We're going to be left with 176,800 minus 170,680 equals 520 Vs. On the left-hand side of the equation, we have left 6,120 equals 520 Vs. Divide both sides of the equation by 520, and you're left with Vs equaling to 11.8 meters per second. We need two sig digs in our answer, so our final answer is going to be Vs is going to equal to 12 meters per second. Application: the Doppler shift. The Doppler effect can be used for any wave, sound, light, etc. The change in frequency and the resulting change in wavelength is called the Doppler shift. Radar guns use the Doppler shift to determine the speed of an oncoming car or the speed of a pitch in baseball. So again, an example of the Doppler shift would be the difference between the wavelength and frequency experienced by person A compared to person B. Since the vehicle is moving towards person A, there's a shift in the wavelength as well as the frequency of the waves that the person is encountering. Supersonic travel. Objects traveling at speeds less than the speed of sound are moving at subatomic speeds. For instance, hot air balloons move at subatomic speeds. Objects traveling at speeds equal to the speed of sound are moving at what's called Mach 1. Objects traveling at speeds greater than the speed of sound are moving at supersonic speeds. If you're at the speed of sound or greater, sometimes you're going to be given a Mach number as your speed. So a lot of planes can travel at Mach 2 or Mach 3. Mach speed is simply a multiple of the speed of sound in that particular medium. So for example, if the speed of sound in that particular medium was 332 meters per second, Mach 1 would be 332 meters per second, or 1 times the speed of sound. If the object was traveling at 664 meters per second, that would be considered Mach 2, 996 would be Mach 3, etc. But you got to keep in mind the speed of sound does change depending on the medium that the sound is traveling through. Now a couple of examples of Mach speeds being reached. The F-22 Raptor can reach speeds of Mach 2.2, or about 2,410 kilometers per hour. And upon re-entry, some space vehicles can exceed Mach 25 and as a result, create a fireball as they're passing through the atmosphere. Check your understanding. At an altitude of 10 kilometers, the speed of sound is approximately 1,060 kilometers per hour. What is the Mach number of an aircraft flying at an altitude of 10 kilometers with a speed of 1,800 kilometers per hour? Pause the video and try the question. Now, since we're just simply looking for a multiple of that speed of sound, we don't need to convert everything to meters per second because they already are in the same units. We have kilometers per hour and we have kilometers per hour. So to find Mach, we're going to take the speed of the aircraft, let's call it speed aircraft, divided by speed of sound. The speed of the aircraft is 1,800 kilometers per hour, and the speed of sound is 1,060 kilometers per hour. The kilometers per hour cancel out, and you're left with 1,800 divided by 1,060, which equals to Mach 1.7. It's going 1.7 times the speed of sound. Check your understanding. What is the Mach number of a plane traveling at 1,836 kilometers per hour in an air temperature of 12 degrees Celsius? So same idea as last time. Pause the video, try the question. So once again, our Mach number is going to be the speed of the aircraft divided by the speed of sound. The speed of the aircraft is 1,836 kilometers per hour, but we don't know the speed of sound in this example, so we got to figure it out. We're told the temperature, and we can use this formula right here to figure out the speed of sound. So V is going to equal to 332 plus 0.59 times 12. That equals to 339.08 meters per second. Now we need to get it in kilometers per hour. So we're going to multiply that by 1 kilometer over 1,000 meters. And we'll multiply that by 3,600 seconds per 1 hour. The meters are going to cross out, the seconds are going to cross out, and you're going to be left with 339.08 times 1 divided by 1,000 times 3,600 divided by 1, which equals to 1,220.69 kilometers per hour. So we'll put that into our equation up here. The kilometers per hour cross out, and we get a Mach number of 1.5. And again, unitless because the units cross out. Supersonic travel. So regarding the sound waves, what happens when the speed of the aircraft reaches the speed of the sound waves it produces? And what happens when the aircraft's speed exceeds the speed of sound it produces? So for example, what happens if an airplane travels at approximately 332 meters per second? Or if it travels at 400 meters per second? So check out this video to find out the answer. Now what we need to keep in mind is that aircraft are going to emit sound in all directions. So if it's stationary, our aircraft is going to emit sound waves uniformly in all directions. But if it's moving, like in the case of this plane right here, so in this case we're moving to the right, what's going to happen is that those sound waves are going to get bunched up at the front, because every time it emits another sound wave, it's already catching up to the previous one it already produced. And that causes a compression of the sound waves, and that's what we're seeing right here. See how the wavelengths are getting closer and closer together. At speeds equal to the speed of sound, the sound waves pile on top of each other and constructively interfere. So you're just getting a whole bunch of sound waves all being piled right on top of each other right here. So you kind of get this line of sound waves extending up and down. At this point, the plane and the sound are moving at exactly the same speed. So every time the plane emits a sound, it's going to catch up to it and then emit another sound right on top of the previous one. At speeds greater than sound, the sound waves are compressed and pushed backwards in a cone-like shape. So now we can't have the plane in front of the sound waves because it's emitting the sound waves. It's always emitting it in front of it. And think of these sound waves maybe coming from the engine. So what we end up seeing is this cone-like structure where the sound waves are all piling up on top of each other, but the plane's moving at such a speed that it's creating a cone in front of it. So at speeds equal to or greater than the speed of sound, the sound waves pile up and create a shock wave. As the aircraft passes overhead, the sound waves pass you all at once, creating an intense sound, very high decibel, that we call a sonic boom. So if you're standing right here, you're not going to hear anything. But as soon as that plane passes over your head, and now you're standing like this, it's going to be a very intense amount of sound hitting you all at once, kind of like a wall of sound. And this is a very big misconception. Most people think that it's this thing that the aircraft pushes out or passes through, but really what a sonic boom is a sound barrier, a wall of sound that passes over a given area. So instead of hearing the sound little bits at a time, you're hearing it all at once. You're hearing the sound created by the aircraft for the last X amount of time, and it hits you all at once. And that's what we call a sonic boom. And then like I was talking about before, when our aircraft is traveling faster than the speed of sound, we're going to create this cone. And the cone is very unique because you're not going to be able to hear the sound unless you're inside the cone. So very similar to when it's traveling at the speed of sound, you get all those waves piling on top of each other. But until you're actually in this cone, you're not going to be able to hear the sound. So the drawing here is trying to represent a 3D representation where this guy is actually further that way, and this guy is inside the sound. So as soon as that cone passes over this guy, he hears it. But this guy here can't hear anything at all. He can't even hear the aircraft because the sound being created from the aircraft isn't getting to his ears. I'd like you to pause the video and watch this clip here. It's a good look at what a sonic boom is. A vapor cone can suddenly appear as the aircraft approaches the speed of sound. It's simply a condensed cloud of water vapor, and the cloud appears due to the sudden decrease in temperature around the wings caused by a rapid drop in pressure associated with very high speeds. So when the plane is moving really fast, what happens is that you can get different air pressures on the wings, and depends on the atmosphere it's flying through, you can get a really sharp drop in pressure. As you do, you can get this cloud forming. It has nothing to do with the sonic boom. The only thing they have in relation to each other is that you need to be traveling pretty fast in order for it to happen. And that concludes our lesson on supersonic travel and the Doppler effect.